Okay, thanks for the invitation. Let me first briefly recall the Burton-Swinnerton dial conjecture. So suppose E over Q, defined over Q is an elliptic curve. And suppose the conductor is an integer n. And associated to E, there is a L series, which I guess is already defined in yesterday's talk. By this Taniyama-Shimura conjecture, which is now already a theorem, we know this is actually an entire function for S in the whole complex plane. And also we have the model way group, which is defined to be the set of rational points of E. Okay. And another arithmetic invariant is called the SHA group, Shafarishi-Tate group. We use this symbol to denote. So it's defined using Galois cohomology. I think in previous talks I've already seen this several times. So the BSD conjecture has two parts. The first part is called the rank part. So if we define the analytic rank R to be the vanishing order of this L series at S equals 1, recall that this is the entire function, so we can talk about the analytic property at any point. So the conclusion is that this is equal to the rank of the model way group, which is finally generated abelian group. Okay, so this is the rank part. And the second part is called the full BSD. It gives the leading Taylor coefficient of this L function at S equals 1. So the formula is the R's derivative divided by something. I will explain the notation in a moment. R factorial times the period omega E and the regulator RE. This is equal to the cardinality of the Shafarishi-Tate group times a product of some local invariant called the Tamagawa numbers. This is a simple local invariance divided by the torsion part, the cardinality of torsion part of the model way group and taking the square. So here, omega E is the period of E, and R is the regulator map defined using the height pairing. It's the determinant of height pairing. So they are normally transcendental numbers. But the point is, although the numerator and denominator are usually the transcendental numbers, however, if you take the quotient, then it's going to be a rational number, and it has an arithmetic meaning for that. Okay. So what's known about this BSD conjecture? Well, so nowadays the known cases are mostly for R equals 0 or 1. Then the rank, in this case, the rank part is known. Well, this is by the work of Grosdagier formula and Kolyvagin's work. And if R is at least 2, then very little is known. So the hard part is people don't know how to show the finiteness of this Shafarishi-Tate group, although its conjecture is finite, but it's extremely difficult. So so the reason to that it's easier in the R equals 0 or 1 case, because in those cases you have very explicit ways to construct rational points on the elliptic curve over some quadratic imaginary field. So that makes the study much easier. But if R equals, so those points are called Heegner points. But if R is at least 2, then if those Heegner points turn out to be torsion points, so you don't get non-trivial elements in the model way group. And if R at least 2, so I guess only just can do some case-by-case study. So just know a few very single examples, and there's no general theory for that. R equals 0, yeah. Yeah, R equals 0 is doable, yeah. Yeah. 0 or 1 is, and today we're going to focus on the case when R equals, so the part 2, so I should say the part 2 is called the full BSD. I'll focus on full BSD, I mean part 2, when R equals 0 or 1. And in those cases, it's also known that both hand sides are positive rational numbers. So an observation is that in order to prove full BSD, it's enough to prove the p part of both hand sides are equal. In other words, the maximal p power divisor of both hand sides are equal. If we know that, then we know part 2. So the p part of both hand sides are equal. So that motivates the p-adic method. So an important tool to study this problem is the USR theory. Which you can think of studying those kind of relations in p-adic families. And in fact, there are, in principle, there are 2 approaches to study USR theory, the p-adic USR theory. So the first approach is called the Euler systems. So using Euler system, so it's especially useful to deduce the upper bound of the arithmetic side, meaning the size of the arithmetic side is at most that large, predicted by the L value. A second method is the automorphic form approach. So this originated from early paper of Ribet, and such argument is sometimes called a Ribet's lemma, but nowadays it has been very complicated. So, and the automorphic form approach is to give the lower bound of arithmetic size. So these 2 approaches altogether should give the required result. And now let's talk about some results on this BSD formula. So let's first discuss the CM cases. So this case is relatively easier to study because they are reduced to study Higgs character of quadratic imaginary field. So they're basically class field theory, and you have so basically it's some kind of abelian object. So for odd primes of odd primes P, so essentially the P part of BSD when R equals 0 or 1 follows from the USR conjecture. And which is proved by Carl Rubin using this Euler systems of elliptic units. So in this case, one doesn't need to use automorphic forms because you have the class number formula that combined with this 1 bound from Euler system will give you full equality for the USR conjecture. I should also remark that, so in general, the BSD formula follows when R equals 0 follows from the USR conjecture, but R equals 1 case doesn't follow from that. But in the special case of CM elliptic curves, because we know that the p-adic regulator is non-vanishing, so in this special case, one still can deduce the BSD formula in the R equals 1 case from the USR conjecture. So of course, this also involves some work of Perrin-Real on that, so in order to know the full BSD, you just need to study something, study the problem for p equals 2. And in this case, there are some partial results on that. For example, if r equals 0, then the Chunlai Zhao had checked some. So in 1997, he checked the two parts for certain infinite families. Checked for certain infinite families. Therefore, deducing this full BSD, and if r equals 1, there has been this breakthrough of Yetian on this congruent number family. So that's a special family of CM curves, congruent number family. So they are elliptic curves defined by this equation y squared equals x times x squared minus n squared. When n is varying, it's varying in a CM family of quadratic twists. And so in that case, you have this. There are well, actually, two part has been studied by Ye Tian and Shou Zhang. Well, Xin Wan and Shou Zhang, and there, so that deduces the full BSD in those cases. Actually, there are some other work needs to be taken care of. So that's the work of Cai. Liu, yeah. Liu should, yeah. Yongxiong Li, the last speaker. Liu and Ye Tian. So in those cases. So in fact, it's remarked by John Coates in a survey article in 2013 that for CM elliptic curves, it's hopeful that techniques can enable us to work out all the cases for all the CM cases for BSD. So hopefully in a few years the full BSD for CM cases will be within reach. But now let's turn to the non-CM cases. So this case is more difficult to study. For the main reason is it's no longer a Higgs character of some field. It's honest GL2 object, and so you don't have this. You cannot use this class number formula to simplify the problem, and you need both the Euler system method and the automorphic form method to deduce both the upper bound for the Shah group and the lower bound, and combine them together to get the P part of BSD. And so as you said previously, only a finite number of only know for BSD for finite number of non-CM elliptic curves. And this is by computer check. Because in r equals 0 or 1 case, you can actually use computer to get both hand sides and to check if they are equal or not. But now we have general theoretic results. Let me list a few theorems here. The first theorem is for the P part. It's due to many different people. I will first state the result and then list all the names. If r equals 0 or 1, I suppose P does not divide n, and suppose moreover that the mod P Galois representation from the Tate module is absolutely irreducible. representation. That again, this mod P representation, but you restrict to some finite, some decomposition group at some finite place is ramified for some L. Dividing n to the first power, then then the P part of BSD is true. So the statement of theorem is like, oh well, she's out prime. Sorry. So the statement of theorem is slightly different from what's stated in the papers, but actually it's slightly more general, but actually is provable. This theorem is due to many different people. First of all, Kato. So he constructed all that system for GL2 modular forms, proving the upper bound of the SHA. So basically he proved the USL conjecture, I should say. And that deduces R equals 0 case. One-side divisibility, sorry. And Skinner above, they proved this the other side divisibility in the USL conjecture in the ordinary case, and also by myself, I proved the super singular case. The USL conjecture for in the super singular case, and also there's Wei Zhang, he proved R equals the BSD formula R equals 1 in the ordinary case, and differently by my joint work with Dimitar Jeshev and Chris Skinner. Yeah. So we use a different method to prove the BSD formula when R equals 1, which including both ordinary and super singular cases. I should also say that this flowing Sprung. Basically, in my proof for the super singular case, I assume the AP equals 0, but there is if AP is not equal to 0, then Sprung proved that the case following the strategy of my paper. Okay. And this is the first theorem. Let's call it theorem 1. Now that we have theorem 1, let's try to let's state the second theorem. So this is for the P part. So now how about for the full BSD? In other words, we need to take care of all primes P. We have this this theorem. So first let E be a semi-stable elliptic curve. Conductor is n. So let m be a square-free, be some square-free integer. And we write em for the quadratic twist, for the twist of E by this field extension, root m over q. Now we put some assumptions. Sorry. Well, first we assume EP as a restricting of GQ is absolutely irreducible as before. Actually, that's already required by Kato's work for all other primes P. And secondly, we will assume that LEM 1 is not equal to 0 and the two part of BSD for EM is true. Thirdly, we assume there are primes Q1, Q2 dividing N such that for all odd primes P. So it turns out, okay, all primes P, odd primes P, there exists a Q equals either Q1 or Q2 with Q not equal to P such that the modular P representation restricting to GQ is ramified. And this, the assumption, the motivation for this assumption is clear from the statement of theorem 1. And finally, we assume that M is only divisible by primes where E has good ordinary reduction. So it is known that the set of prime has density 1. Okay, so that's already earlier observation by Sayre. And we also assume that M is prime to 105. Then the conclusion is for BSD for EM is true. So this assumption, so all the assumption except the second one is checkable from this database. And how about the second assumption? Well, there are recent work by many people on this Goldfield conjecture. Or weak Goldfield conjecture, something like that, and the two part of BSD. By many people whose name are now listed. So this work by Daniel Chris and Chao Li and and Cai, Li Cai and Chao Li and Zhai and many people. So they had recent results on two parts of BSD. Well, so let's call it theorem. Oh yes, it's theorem 2. By their results and the theorem 2. We have the following corollary, which says that for E in the following list, there is a explicitly defined explicit set of set we call it ME of primes with positive density. Such that for any square-free product M of primes in ME, we have this analytic rank of E twisted by M is equal to 0, and the 4 BSD for EM is true. So I haven't told you what's the list. So we use the Cremona label. So I will list the field. So for example, conductor 46, 69, 77, 85, 94A1, and so on. So in other words, we have many examples. In fact, we have checked the elliptic curves for conductor, so the E, for elliptic curves E of conductor up to 165, and we found 20 such kind of infinite families, so that the full BSD is true. So that provides many examples of elliptic curves satisfying BSD. Actually, it's much more than in the CM cases, because CM cases can fit in a finite number of such kind of infinite families for quadratic twists. But here we have in the small conductor case, we already have many examples. Of course, the statement of the theorem, the assumptions for theorem 2 is still there should be a large room of improvement for that, which is some work we have been working in progress. For example, so this is R equals 0 case. One certainly has a similar case for R equals 1 case, and also there are ways to relax the assumptions put in there. For example, we may try to relax all the assumptions on the ramification. So here, for example, let me draw a table on what's going on with all the primes P in this theorem 2 and the corollary.
The third assumption.
Third assumption, which theorem 2?
No, theorem 1.
Theorem 1, okay. EP restricted to GQL is ramified for some L dividing n to the first power.
Yeah. Where is the assumption coming from? Can you explain?
Where is this coming from? I mean, for example, if you look at the Skinner advanced paper, that's already put there. So that's a technical assumption put there. So you have to. So that's used to. I mean, that's a technical point. That in the proof you need to prove that the P-adic function has anti-second atomic mu invariant 0. So if you want to prove that, you need to assume that. Yeah. Actually, it's also it's also required by Kato solar system argument. In that you do need to have a the Galois representation must have an element in the image which has unipotent image modulo P. Yeah, that's so there are multiple reasons for putting that. Okay, 1, 2, 3, 4, 5. Okay, so this is P. So if P equals 2, as we said, is Chris, Charlie, and Cai Li Zhai. And if P is good ordinary, I should say that assumption is, if you assume it's semi-stable reduction, that this is automatic. Good ordinary reduction, this Kato and Skinner are bound. And it's super singular. So this is Kobayashi, and myself, and Florian Sprung, and multiple reduction. So in this case, actually, at P the elliptic curve is actually ordinary. So, and Skinner used the variant of his work with Alban to prove this case when this has multiple reduction. And in this case, and also you have additive reduction because you're taking quadratic twists. So add those twisted primes, and the elliptic curve has additive reduction. But in this case, we have made the assumption to make the situation very simple because it's a twist by a character of some good ordinary case. So they're still nearly ordinary case. So we can revise Skinner-Alban's original argument. Of course, there are technical points in that, but that's doable. So that's done by myself. So that we have treated all the cases. And one thing to we had some idea to work on is to, for example, to relax all the assumptions on ramification. We should be able to allow, in general, additive reduction primes. But yeah, and so now. That's for elliptic curve case. Of course, those results can be generalized to modular forms because elliptic curves are some special case of modular forms of V2, and we have general weight modular forms. Now let F be a Caspil eigenform. Suppose the weight is 2k. We assume the weight is a even number because we want the central value to be an integer. A central value is just the s equals k. And the conductor is n. And suppose p does not divide n. P is a odd prime. And we have it's well known by many people that there is a associated Galois representation to GL2 OL. Well, O is the integer ring of some L, which is coefficient field, which is finite extension over QP. And again, we have this L series associated to that. And the central point of the functional equation is S equals K. So now suppose LFK is not equal to 0. In other words, we are looking at the R equals 0 case. Okay. The theorem is, let's call it theorem 3, is that, well, so the LFK divided by omega f. So you can still define a period. And that in the R equals 0 case, there is no regulator there. This is equal to the cardinality of the Schar group. Well, sorry, I shouldn't write that. I should write they are equal up to a p-adic unit. The cardinality of the Schar group. In this case, the Schar group is just the Selmer group, which can be defined using Galois cohomology. And again, you have a cohomological definition of this Tamagawa numbers there. And so this means equal up to a p-adic unit. I should say, assume 2k is at least less than p. That means it's in the Fontaine-Lafayette range. So this theorem is deduced from Iwasawa-Mon conjecture. However, to prove the Iwasawa-Mon conjecture, we don't need this assumption. Even in order to have a nice formulation for this BSD formula in general, we do need to put this Fontaine-Lafayette range assumption. That's for some local, p-adic Hodge theory reason, and for some reason about this comparison isomorphisms. So that's for R equals 0 case. And how about for R equals? How about the R equals 1 case? Well, I should say there are some. Under some technical assumptions. Well, because I don't want to have time to state under some technical assumptions. Just an analog of this kind of thing. So it's theorem 4. This is a joint ongoing work with Dimitar Jeshev and Chris Skinner. So assumptions are in theorem 3. Theorems 3. But we assume this R equals 1. So this is R equals 0 case. We don't want this assumption. This time we assume R equals 1. And so we need another assumption. Suppose that, so we have this, suppose the Chow group, the higher Chow group of some Kuga-Sato variety. We write Kuga-Sato variety to be, Ks is injected into this Stammer group. I should say the F eigencomponent, because we have an eigenform F, so we can talk about the eigencomponent for this Chow group, and for the Hicks correspondence. So suppose this map is injective. Under the Abel-Jacobi map. So this is the Abel-Jacobi map. Then we have L prime Fk divided by omega F Rf. Again, the regulator maps equals the, up to a p-adic unit, it equals the cardinality of the Shah group times the product of Tamagawa numbers. I should say, under those assumptions, there should be a denominator here, but under those assumptions, the analog of this torsion part of the model A group is actually trivial. And we should say that actually this is a very serious assumption. This is very restrictive. Without this assumption, it's not even clear how to have a nice definition for this regulator map. And this, so this assumption is a special case of Beilinson-Bloch conjecture. So Beilinson-Bloch conjecture. So it's not very satisfying, but we have to assume this thing for various reasons. And there is another version of this theorem which uses the so-called Heegner cycles. So recall that in the elliptic curve case, we can reformulate the full BSD reformulate the BSD conjecture using Heegner points. Yes. So recall that suppose let kappa E be the Heegner point. Then suppose R equals 1. Then BSD formula is equivalent to the statement that the index of so we take a quadratic imaginary field. So in this case we take sorry, let me rewrite everything. Let K over Q be a quadratic imaginary field. And suppose this R, the R for LE, but over K is 1. And then, and suppose kappa E is the Heegner point. So if R equals 1, then it's known that Heegner point is not torsion. Then the BSD formula for K, for E over K. So in fact, if you know the BSD formula for E over K, then there are some techniques to deduce back the result for Q from the result over K. Is equivalent to the fact that the index So I'll tell you what's that. So this is the index P over Q. So the index of Heegner point. Take the square is equal to the cardinality of the Schar group of E over, by this time over K times the product of the Tamagawa numbers. Of course, I mean, under those assumptions, I totally ignore the denominator here because under those assumptions, we assume that torsion part of the modular group to be trivial. So this is by the Gross-Zagier formula. So Gross-Zagier formula basically said that, what's P? P is the generator of this rank 1 model weight group of E over K. So what Gross-Zagier formula tells you that the derivative of this L series for E over K divided by this height pairing of the Heegner point is equal to yes. Well, I should say, so is essentially equal to the height pairing of this Heegner point. And if you look at this, the BSD formula, so the regulator map. The regulator R is actually equal to height pairing of P. So if you divide it by the regulator, means divided by the regulator by the height pairing of P. And so what you essentially get on the left hand side is just the square of this index of K. Index of Heegner point in the model weight group of E over K, and the right hand side is nothing but this arithmetic invariant. So actually the BSD formula is reduced to proving something like that, and we have an analog result for general modular forms. So in this case, we put a assumption which looks better than the special case of Bayes-Bloch conjecture, which we call it assumption star. We assume that so let kappa f be the Heegner cycle. So that's the analog of Heegner point. However, it's a Heegner cycle on this spatial cycle on the Kuga-Sator variety, and it's actually a higher dimensional cycle. Instead, so Heegner point is a point. This is a higher dimensional cycle. Assume that the image of the Heegner cycle in this Selmer group TF is non-torsion. So this assumption is reasonable because Nikolvar proved that under this assumption, this Selmer group should be rank 1. So this is some assumption that we cannot avoid, and it's a reasonable assumption, which looks better than this Bayes-Bloch conjecture thing. And under this, we prove that we call it theorem 5. The square. Let me use word. The square of the index of a Heegner cycle in H1F kappa TF. So here I'm having a bit ambiguous because we actually realize this TF in this entire cohomology of the Kuga-Sator variety is equal to the Schar group. Actually, the Schar group is defined by this torsion part of the Selmer group. Maybe it's better to write the other way. Fk, the torsion part, and times the product of Tamagawa numbers up to a periodic unit. Okay, I think I'll stop now. Yes.
How about the other critical values? So
How about other what?
other critical values. So you work on the
So
yeah.
yeah, central point. You mean
Central values. So how about other values?
other
Critical
other point? Yeah. I mean, so the thing is, I can prove this as long as it's sitting in the periodic family passing through the central point. I can prove the US-Salmon conjecture that using some control theorem, I can prove this formula, other critical values. But I have to assume that it passed through the central point, the periodic family, because in the proof we have to use some spatial value result, or it's only available for the central value. So that's like Minlun's result and the Nick-Vassar's result. So I have to assume that it passed through the central point. Yeah. Yes, so actually, theorem 4 is deduced from theorem 5. We've proved theorem 5 first, and to go here, go from there to here is just using this Gross-Zagier formula. Actually, Shou Zhang proved this Gross-Zagier formula, provided the Heegner cycle lives in a modular curve instead of Schummer curve. Yeah. So actually, so at the moment we need to put assumptions to guarantee that. However, so recently I attended a conference in Xin Wan and met with Shou Zhang and some of his students. It said they had some people. They said it should be the Schummer curve case should be doable, and they had students working on that.
Okay, so let's try to speak on this.